Okay, good afternoon to everybody. Good morning for people in America, and good night for people from Asia. And okay, it's a big pleasure to introduce Liliana Pasquale from University College Dublin and Lero, and she's gonna give the keynote on towards formalizing sustainable security systems. Okay, please. Okay.
Hello, everyone. So the purpose of this talk is not really to provide answers, but rather to provide questions that the formalized community can hopefully address. And thank you for the introduction. So my talk will be divided in three parts. In the first part, I will give an introduction to sustainable security, which is quite a novel concept, also in the software engineering area. I will also provide an illustration of three key ideas that can be used to support sustainable security. And finally, I will conclude by providing a roadmap. So let's start with the first point, an introduction to sustainable security. So the notion of sustainability has been already proposed in the software engineering community. So for example, in the paper written by Venters et al., software sustainability has been considered as the capacity of a software system to endure. And contribution in the software engineering domain have been divided in two groups. Contribution aimed to build sustainable software, and that software that, for example, approaches that provide principles, practices, and processes that contribute to the software endurance. And other work that instead focused on software engineering for sustainability, which stands for building software systems that support one or more dimensions of sustainability. For example, software that support environmental sustainability or economical sustainability or individual well-being. So this talk will focus on this aspect of sustainability. So the objective is to build software that can endure, and in particular can endure security properties. So sustainable security is considered as the capacity of software to endure satisfaction of security requirements. So if you think about this, one properties that come into mind is the property of autonomy. So in order to endure satisfaction of security requirements, software system should autonomously reason about threats and counteract such threats. However, this is not very easy. It's quite difficult, especially in cyber-physical systems. So what I'm going to do now, I'm going to give you an example of a fictitious cyber-physical system, just to give you an idea about why sustainable security is difficult in such system. Imagine that we have a warehouse, a smart warehouse of the Zephyr company, which is a pharmaceutical company, and this is the plan of the smart warehouse. And there is a receiving area where drones are used to scan RFID tags associated with products and place this information in an inventory database. This smart warehouse has different storage zones where robot driver units are tasked to store different drugs in different storage zones. For example, certain drugs like vaccine are stored in storage zone 3 because it's cooled. And finally, we have another area where a human operator can communicate with a mobile human-machine interface to, for example, control the robot operations. So this is the structure of this cyber-physical system. However, in this cyber-physical system, it's very hard to reason and counteract threats that are brought by an extended attack surface. So what does it mean, an extended attack surface? Means that the attacker are increasingly exploiting the interplay between cyber and physical spaces that characterize the operating environment where software systems operate to cause harm. For example, some of these attacks are considered cyber-physical, Why? Because they exploit vulnerabilities in the cyberspace space in order to cause harm to physical assets. For example, imagine you have an attacker that connects to the network, and because the doors are controlled through the network, is able to lock the RD units in storage zone 2 that is not cooled and contains the vaccine. So this can cause deterioration of the vaccine. Another example are physical cyber threats. So physical cyber threats, for example, exploit physical properties of the space to cause harm in the cyberspace. For example, the fact that a human operator is collocated with the human-machine interface allow him or her to tamper with data about drugs that are stored in the inventory database. So intuitively, to reason and counteract threats brought by an extended attack surface, it's necessary to explicitly represent the structure of the space and the cause-effect relationship between events that happen in these two spaces. The second reason why sustainable security is challenging is that it's very hard to handle uncertainties that are brought by unexpected threats. So unexpected threats can be brought, for example, when new vulnerabilities are discovered. And there are always zero-day vulnerabilities. New vulnerabilities arise all the time, and it's necessary to be prepared and counteract them. Imagine in our example that a machine programmer is working on an engineering workstation and to, for example, update the behavior of the robots, for example, to store drugs that are ordered more often on the top of storage zone 3. So in this case, the machine programmer can introduce vulnerabilities that, for example, increase the temperature of the storage zone 3. And this can be due to the fact that the change in the code was affecting the behavior of the robot in storage zone 3. So in this case, what can we do to handle uncertainties brought by unexpected threats? Intuitively, a software system should be engineered with the capacity to discover and counteract threats while they are in operation. Finally, the last point, why it's difficult to engineer sustainable security, is that it's very hard to endure stakeholder engagement. And stakeholders play an important role in security. For example, stakeholders can be software engineers that introduce vulnerabilities. But in this talk, we focus on human operators that have to interact with the cyber-physical system to perform their work. As an example, and these human operators sometimes need to take security-relevant decisions on behalf of the system itself. So imagine in this example, there is a dangerous content spill in storage zone 2. In this case, a human operator might be involved in deciding to, for example, lock access to storage zone 2 temporarily until the problem is solved. So it's necessary to provide ways to involve human operators to understand the behavior of the system and what's happening so that they are capable to take security-relevant decisions. Okay, so another thing I wanted to clarify before I move ahead is that there may be the impression that sustainable security is the same as adaptive security, in the sense that the software system needs to continuously adapt in order to counteract threats. However, sustainable security, although it includes aspect of adaptive security, it's more than that, because, for example, it requires to produce an approach to discover and counteract new threats that were unexpected before, and also requires to provide tailored explanation to stakeholders in order to foster the engagement in taking security-relevant decisions. So that's the main difference, which I believe is between sustainable security and adaptive security. So I hope that right now you are on board with me and you are convinced that sustainable security is important, and I hope you will think in your research agenda about what can you do to support sustainable security. And what I want to do here now is to just give you a brief idea. It's not exhaustive because there is a lot of literature available, but just focus on three key ideas that can be exploited to support sustainable security. And these three key ideas will touch the three challenges that I described before: how to formalize and reason about the extended attack surface of a cyber physical system, how to discover and counteract new threats, and how to provide explanation to human operators that make them on board and able to take security relevant decisions. So let's start with the first point. So how can we formalize and reason about the extended attack surface of a cyber physical system? The key idea is to express the topology of the space. Topology refers to the study of shapes and spaces, including properties such as connectedness and boundaries. But in this talk, we will refer to topology as representing A, the structure of the space, B, the location of objects and agents in the space, and relationships such as proximity and reachability. So what is topology in the end? If we consider our example and we think about the structure of the space, can represent the connectivity of physical area. For example, we need to represent the fact that, for example, storage zone 3 and storage zone 2 are connected because the connectedness between rooms can cause attacks. For example, the fact that a robot can enter an area where there is a dangerous content that's spilled. The other aspect is that it can also represent connectivity of digital areas. For example, the fact that the wireless allows connection to the doors that can open using software programmatically. So, and this aspect facilitated the attack that allowed to lock the robot, the RDU, inside the storage zone. So another aspect is the location, the placement of objects and agents. So, for example, it's important to think about when an RDU is transporting, is collocated with the vaccine. Or another aspect is the proximity, collocation in the same area. For example, we want to think about situation when a human operator is collocated with a human-machine interface and can, due to this relationship, for example, tamper with data that this mobile HMI can access. And also, reachability can refer to accessibility to physical areas or objects. For example, it's important to know that, for example, a specific storage zone can be accessed from, for example, storage zone 2 can be accessed from storage zone 1 and storage zone 3. And it's important to reflect about this relationship because, for example, if there is some dangerous material, what we want to do, we want to block access to this area. So, and finally, reachability can also refer to digital object and area, as I was explaining before. So the fact that the wireless is connected to the doors also allow an attacker who gain access to the internal network to potentially control the opening and closing of these doors. So explicitly representing these characteristics when we represent a system will allow us to reason about potential attacks and identify security controls. So what a formal language should have to represent the topology? So it should represent the structure and the communication. So it should represent the topological characteristics that I described before, and also should be able to enable reasoning about the effects of topological changes. So, in other words, the dynamic evolution of the system. So, we, in our previous work, we look at different process calculi. Process calculi are well-established mathematical languages with well-defined semantics that allow reasoning about properties of concurrent and communicating systems. For example, PyCalculi was one of our first options. So, for example, PyCalculi allow to focus on process migration, interaction, and communication via dynamic channel. We also consider ambient calculus. Ambient calculus was proposed by Cardelli and Gordon and assume a hierarchical spatial structure of processes while imposing the constraint that computation is only encoded as modifications of this spatial structure. However, the main problem of this formalism is that PyCalculus, for example, don't represent the structure of the space, and ambient calculus, for example, don't allow to represent only all the characteristics of the cyber-physical space. So we consider another language, which is a bigraphical reactive system that was proposed by Robin Milner. So bigraphical reactive system it was a good formalism because allowed to consider both the communication and the structure, and also allow to define the dynamic behavior of the system. For this reason, in our previous work, we consider bigraphs and represented the structure of the cyber-physical space using bigraph and use them to reason about potential security threats. I just want to also to clarify that bigraph is not the only way in which we can represent the structure of the space. I bet many of you are familiar with the spatio-temporal logic, for example, formalism that extend the signal-temporal logic to describe properties of the space. So in this talk, I'm just focusing on the work I did together with my colleagues. But I want to also acknowledge that there is other work that can express the properties of the cyber-physical space. So what are bigraphs? So bigraphs are characterized by place graph, which is basically a forest of trees and allowed to represent nesting. This is very good to represent the physical structure of the space. While link graph is basically an hypergraph that represent a relationship over the nodes that were expressed in the place graph. And this allows us basically to represent many-to-many relationships among nodes. For example, communication relationships among nodes. So I just want to give you an idea about the notation of bigraphs and how we can use it to represent our example. For example, bigraph allow to represent nesting properties. So this is an example of a part of the smart warehouse expressed using bigraphs. So bigraph allow to represent nesting. For example, we can represent the fact that a robot driving unit it contains a vaccine with the dot notation. Or, for example, we can use the juxtaposition of children to represent collocation in the same physical space. For example, in this case, we can represent the fact that an agent, so human operator, is collocated with the human-machine interface in the same room, for example, the office in this case. Or we can also represent ports. Ports can be used for different reasons, can represent communication relationship, for example, the fact that the Wi-Fi access point is a port called W-Link that represent the fact that other devices are connected to it because they have a port having the same name. Also, ports can be used to identify nodes. For example, an agent can be characterized by a port indicating the name, or a room, for example, Agent Mallory, or a room can be characterized by a port providing the name of the room, for example, Storage Zone 2. Okay, so bigraphs are really good to represent the structure and the communication of cyber-physical system, and also they provide the reaction rules that allow to express the dynamic behavior. Basically, reaction rules express the fact are composed of a redex and reactum, and represent the fact that a portion of the bigraph matching a redex can be rewritten by another portion of the bigraph representing the reactum. For example, we can have an action enter room. Here, the bigraph has also have a graphical notation. And basically, this represents the fact that if an agent is outside the room, is collocated in the same space with the room, then in the next state, if action enter room is performed, the agent is now contained inside the room that is entered. So, and also to adopt bigraph, what we did, we specified the operating environment of a system using the bigraph notation. We expressed the dynamic behavior of the system using reaction rules, and we also specified security requirements as a topological configuration. Basically, a topological configuration described by a bigraph satisfies a property if the bigraph specifying the property can be matched against the bigraph representing the state of the system. For example, we express security requirements as violation of properties. For example, we have a properties express the violation of the vaccine integrity. In other words, this represents the fact that an RDU Y transporting the vaccine, containing the vaccine, is stuck in a room that is locked, but it's not cooled. So this is a way in which we can represent the violation of security requirements. So security requirements can be expressed in branching temporal logic, CTL, and in this way. So it's always globally properties expressed on the negation of the requirements. In this case, we only have one security requirement. So once we have the representation of the security requirements, what's left now is to perform automated reasoning. So to use the reaction rules to identify all the possible ways in which the system can evolve. So in other words, our specification is transformed into a label transition system where each state represents a different bigraph configuration representing the state of the system, and each transition represents different applications of the reaction rules that lead to a new configuration. So basically, in each state, for example, this is a simplified example of a state. We have agent B in room P, agent K in room P, and agent A is parallel with room P. So in this scenario, we can have two actions that can be performed. Either agent A enters room P or agent B enters room K. And these are represented by the two next states. So the idea is that for each state represented of the system represented as a bigraph, the reaction rules that can be applied are performed exhaustively in order to generate all possible configuration of the system. So this process is basically iterated by exploring all the configuration of the system and generating new LTS states accordingly. So this approach is then, after we have an LTS representing the dynamic behavior of the system, we perform speculative threat analysis. So basically, we identify potential violation of security requirements that can take place in the future evolution of the cyber-physical space. And what do we do? To do that, we interpret the bigraphical reactive system over the label transition system. And then what we did, we performed explicit state model checking to discover the state of the label transition system that represent violations. So imagine that the states in red that I'm showing here represent violation of our security requirements. So what we did then, we use these threat results of the threat analysis to identify security controls, and we use different strategies. For example, when a state P that happens immediately before a violation is entered, what we can do, we can disable all transition, all the actions that lead to the violating states, if this action is of course controllable. As an alternative, what we can do, we can enforce the execution of an action that can lead to a safe state and circumvent the violating state. Another thing we could do here is that when a violating state is reached, what we can do. For example, if state C is reached, we can disable all the transition that lead to a violating states and then force the execution of the transition that lead the system to a safe state. So this can be a strategy in which we can identify security controls that can be enacted dynamically to continue to satisfy security requirements. For example, if we go back to this example, one thing that could be performed is to prevent the robots to enter the storage zone 2 that has the dangerous content. Or an example of this strategy could refer to the fact, for example, when the robot is containing the vaccine and should be let out of an uncooled area. So these are intuitive example about what this strategy, how security controls can be computed and how they can prevent or mitigate security requirements violation. Of course, I guess at this point, you already have in mind clear that there are some challenges to do that, especially challenges related to the generation of the LTS representing the whole system, and challenges related to perform model checking on such a big systems. So I'm going to move forward. I'm going to go back to these challenges at the end of my talk. And now I want to move you back to the 3 key ideas to support sustainable security. So we have seen that one of the way in which the structure of the physical system can be represented is to use bigraphs and bigraphical reactive system to reason about this extended attack surface and identify security controls. The second thing we can do here is to identify a way to discover and counteract new threats. So the last 2 aspects have been much less explored. And so what I'm going to do here is I'm going to give you some ideas about things that could be explored. So how can we discover and counteract new threats? In an ideal scenario, what we want to do is to basically, when a new vulnerability is discovered or the environment where our system runs change, we want to perform an update of our system and perform and use, for example, D, which is a model of the system, and P, that represent a set of security properties, to perform threat analysis. So to discover new threats that could be brought by these new vulnerabilities or this environment change, and use the model of the domain, the updated model of the domain, and the security requirements, and the diagnosis, so potential threats that have been discovered, so potential violation of our requirements, to identify potential security controls that should be enacted in the system, should lead to a revision of the model of the system. However, if we look at this diagram, actually this diagram is exactly the same as the life cycle. So this diagram is exactly the same as the diagram that we can use to evolve requirement specification, where the step that supports the analysis is performed using abductive reasoning, and the step to perform the revision is performed using inductive learning. So I just want to give you a brief idea about what these activities are. So abduction is a constructive reasoning process that allow us to identify a set of assumptions that we call delta in this case, which are needed in order to infer a description of the system and the consequence alpha. While induction is a synthetic reasoning process that produces general rules from the collection of specific instances and allow us to expand the description of the system using that we call here D prime to cover such instance. So as an example, if we look at here, abductive reasoning basically start with the description of the system and the properties that we want to satisfy, and aim to identify some delta, some that basically represents the behavior of the system that satisfy the property P. Also, in event system description, abduction is also used to identify basically a trace of events that we call system transition that will prove a given requirement. Abduction has been also used to basically identify positive example and negative example. So in refutation mode, as we can see here, abduction allows the generation of counterexample, which we label delta minus, that will lead to the violation of the property that we desire. In other words, if we are able to find such delta minus example of incoherent transition, this can act as counterexample that demonstrate that the property P is not satisfied. Let me give you an example referring to our smart warehouse system. If we have a description D of the system, formalized, for example, using propositional logic programming, for example, it represents the fact that an RDU is in room 1, the room 1 is connected to room 2, and the RDU wants to enter the room 2. In the next state, what will happen is that the RDU will be in room 2. And we have this property that a dangerous material, we don't want a situation in which a dangerous material is in the room, and as a result, an RDU is inside the room where there is dangerous material. So if we run abductive learning, what will happen is that we will generate one positive and one negative example. The first positive example represents the case in which the RDU enters the second room and where there is no dangerous material, while the second example represents the situation in which the RDU enters room 2, but in room 2 there is dangerous material. So in this example, I represented with the prime symbol the situation in which the status of the system in the next state. Also, it's assumed that if a rule doesn't change the truth value of a proposition, then the proposition remains true. What inductive learning does? Inductive learning takes the example, delta plus and delta minus, and generates the hypothesis. The hypothesis is a refinement of the specification of the system behavior that could explain the positive and the negative example that basically are the refinement of the description of the system that we need to apply, for example, to satisfy the positive example and not to satisfy the negative delta examples. In this scenario, we notice that the revised specification basically refine the rule that determine the entrance. In this case, the hypothesis refers to the fact that our rule was underspecified. In other words, we missed the representation to specify the fact that the arrival room should not have dangerous material in order for a robot driving unit to move to the room. So this was the proposition that was missing from the revised model, from the revision of the model. So the idea is that abductive and inductive learning can be used to refine the specification of the system and to identify, for example, way in which the specification of the system can evolve in order to counteract new vulnerabilities. So the idea is that abductive reasoning can identify situations in which security requirements are no longer satisfied because the model of the system has changed. And inductive learning can help us refine our description of the model in order to counteract such threats. So these techniques have been used to revise requirement specification, but have not been used at runtime to support, for example, threat analysis and to identify security controls. Last but not least, the last key ideas I wanted to describe is what can we do to provide explanation to human operators. So the objective here is that we want to provide explanation of, for example, why a security requirement is violated, so that human operators can support decision making and can take decision. However, this is a very complex problem. So the objective here is that we want to provide explanation about why a system produces certain behaviors. Or in other words, justify why a certain security requirement or another type of requirement is violated. So obviously, providing a human operator with a full model of the system and the operating environment in the current state is infeasible because this will lead to information overload. Okay, so this is not possible. So, and in previous work, we have seen that abstraction has been used to provide explanation. So abstraction can be used essentially to reduce the complexity of the model. In other words, what I proposed in another work with one of my colleagues is to use abstraction to provide a high level of detail only for the aspect of the system that affect the satisfaction of some requirement of interest, while leaving irrelevant aspects underspecified. So basically, in this way, if we provide more details on the requirements of interest, we can pinpoint the elements that are responsible for the violation of a given requirement. This is also aligned with the principle of situational awareness-oriented design that prescribe to provide human operators only with the information that is specific to the relevant goals. And simplified models can indeed facilitate decision-making. Another thing I wanted to clarify is that abstraction has been already used in previous work to provide explanation about machine interface, but has never been used to provide dynamically to provide explanation about why security requirements are violated. So, in other words, what we propose is that when a constraint C is violated, we want to take an initial model of the system, S, and the environment, E, and the constraints that is violated, to select an abstraction techniques that allows to generate more abstract representation of this model, S prime and E prime, that can be given to a human operator. So this is the main objective of this idea. And what we did, we use abstract state machine. The reason why we use abstract state machine to represent the system is that they can bridge the gap between the human understanding of real-world problems and the system implementation. And they can instantiate model abstraction to more concrete elements of the system. So I'm just going to give you a quick example about how abstract state machine can be used to generate abstraction. So an abstract state machine is a set of rules that are conditioned by and can generate updates for states. A state is basically a set of location, and a location is identified by a function and a set of parameters, similar to a programming language, and each location can be assigned values. So if we have a system model that looks like this, for example, we have some rules that regulate the operation of the air conditioning and the heating of the rooms. For example, the temperature should not exceed or be lower than a certain value. And also we have some other rules that regulate the lights. So they decide to switch on the lights when someone is in the room. And we have a certain set of constraints, for example, that define the fact that for each room, we don't want the air conditioning on and the heating on at the same time. For example, there are other rules here that we won't consider. So if we focus on the first rule, and the first rule is violated, one way to generate an abstraction first will be to only focus, for example, on the rooms that generate the violation. So we will start from this model of the system, and we only characterize this for the room that in this case we call Q, that lead to a violation. So this allows us only to focus on the interesting variables of our model. Another technique that can be used is simply to focus on interesting location. So the only location affecting, in this case, the violated constraint are air-conned R and heating R. And in this case, what we do, we only consider the rules in the model that refers to this interesting location. So, and this is the reduced model that we will generate. Finally, we can do another, apply another set of rules and refer to the fact that the value of air con and heating are both on. And so we can specify 3 sets of rules. The first set of rules that set one interesting location to the value observed in the state at the time of violation. Those that set the interesting location to a value that is different from what has been observed in the state at the time of violation. And finally, the rules that are not at all related to the interesting location. So basically, what we need to do is to assert the satisfaction of the first rule, so assign values that allow to satisfy rule 1, allow to violate, negate the rules in R2, and remove completely the rules that refers to R3. So in this case, we will generate this simplified model that basically point us to the main reason for the violation, the fact that the value H and the value K were not set appropriately because for example, the temperature in room Q was greater than the set temperature plus H and also greater equal that the destination temperature Q minus H. So that's this was the main reason why there was the requirement was violated. So the idea is that applying these abstraction techniques step by step, we can reduce the size of the model and provide specific explanation pointing the human operator to the reason why a certain violation occurred. So to conclude, I just want to give you a brief roadmap about what we can do to support sustainable security. The first aspect we have seen is how to formalize and reason about the extended attack surface. So what can we do in this respect? It's very hard to reason about all possible evolution of the system and perform threat analysis. One thing that we could do is to exploit the compositionality of security properties. For example, certain security properties do not require to reason about the whole model, but allow, for example, may require to reason about individual space separately. For example, security properties that refer to a specific room or only to a subset of rooms, or security properties that refer only to devices that are connected to one another. Another aspect that I would suggest to investigate is to explore model-based diagnosis techniques. Example of these techniques are hierarchical diagnosis techniques that have been widely explored in control theories to reduce the computational complexity of the diagnosis. For example, these techniques use suppression of variables, abstraction of values to reduce the complexity of the diagnosis. In the second point, related to how to discover and counteract new and unknown threat, what I'm suggesting is to provide approaches for continuous threat analysis, which is kind of a DevOps fashion, where on the left we have a digital twin that runs in parallel to the real system. And so when vulnerabilities are discovered in the real system, we need to apply approaches that support threat analysis, for example, using abductive reasoning or other techniques, and identify security controls, for example, by evolving the specification of the system, and enact these security controls on the system itself. So this should be a cycle that should be performed during the system operation. Finally, in relation to the provisioning of explanation to human operators, there is a lot of work to do in this respect. But the idea I was suggesting is to use abstraction that could be, for example, formalized using abstract state machine to create a collection of abstraction strategies that can be systematically selected to provide explanation. And the challenge here is that it's necessary to how can we select a suitable level of abstraction? This can depend on different factors. For example, it can depend on the cognitive abilities of the human operators that has to make a decision, but could also depend on the time available to a human operator to make a decision. And so the idea is to be able to develop techniques to strategically identify an abstraction strategy, and also the order in which these abstraction strategies should be performed, because this could also lead to different results. This is kind of similar to the order application of proof strategies in theorem provers, which could have the same difficulties. So this is to recap. So these are the 3 main points that I wanted to highlight in my talk. And finally, I hope you will reflect on them and will address them in your research agenda. And I just wanted to, these are the references of my talk, and I just wanted to thank you for listening me. Thank you.
Okay, thank you very much, Liliana. It was extremely nice and clear talk. So, okay, we have already some questions, so just brief now, and okay, so now brief this, after talking so much, we are live, okay, now? We are live now. And, okay, so can you explain more what exactly cannot be represented by PyCalculus? This is the first question that was raised.
Yeah. Okay. Oops. Okay. So the difference is that PyCalculus assumes a structure of processes. So does not explicitly represent in the semantic of the language the structures such as containment, collocation, which are something that are provided in the language of bigraphs. So the properties of bigraph could be represented in a different formalism, in a different way, though. It's just that bigraph provide them by default in the language, in the construct of the language itself.
Okay, and then again from the same simple person, another question: what would be the challenge, limitation of conventional model checkers supporting CTL to model such scenarios?
Yes. So the problem here is that the main problem is the size and the complexity of the model of the system, and especially in cyber physical system, the main challenge is the fact that they are large scale, and so the model checker adopt techniques to optimize the verification, but these are not sufficient when we are dealing with such a large-scale system. So we need to find other ways to, for example, exploit the compositionality of the properties, or find other ways to reduce the model in order to facilitate the reasoning. The second aspect is that this reasoning must be performed at runtime. And so there are additional challenges related to that. I cannot hear, sorry.
I am muted while you are talking, sorry. It seems that you are still verifying simple reachability properties, while for security, often equivalence properties are more interesting. What is your perspective on this? So, okay, equivalence properties to...
Sorry, I didn't understand the question.
Okay, so, okay. Mohamed, okay, is asking, it seems that you are verifying some kind of simple reachability properties.
Yes.
While for security, often equivalence properties are more interesting.
So maybe Sardar, no, Mohammed, can you clarify what you mean for equivalence properties?
We ask for him. So Mohammed, if you write down.
I can answer the next question. So
yes, right.
So yes, the Thule techniques actually we use for a forensic readiness approach, but I use the ISP for abductive reasoning and ILP for inductive reasoning. So there are tools available to perform both tasks. And actually, the new tools that performs inductive reasoning, so like inductive learning approach, are quite optimized and are a better performance at runtime.
Okay. And Claudia is saying nice talk. And when applied to the security domain, have you experienced or think that there are also challenges related to the underlying reasoning mechanism of the FM algorithm, like scalability, performance issue?
Yeah, so I mean that's the main problem is that there could be strategies to perform runtime verification, but so for example, it could be something similar. So what we did was to use some concept similar to bounded model checking, in a sense that we perform the verification up to a certain look ahead. And reperform the verification afterwards. So every time we only perform the verification up to a certain number of following states. However, so there are. I acknowledge that there are many approaches to reduce the complexity of formal analysis. For example, the abstraction has been used in model checking. There is a nice survey on how to reduce the complexity of formal analysis in software product lines. But the main point is that these need to be there needs to be other ways to reason about security properties. For example, exploiting and using in a more strategic way the structure of the space and how this can provide information on the aspect of the models that are more relevant to verify a security property. So this is my main point.
Okay. And Mohamed was adding, he is asking to come on stage, but we cannot. Okay, I was invite on stage people in the audience. This can only be done later on in the discussion room. But his example for equivalence properties was, for instance, two trace properties which are with indistinguishability, privacy properties, and this kind of property that are. But maybe, okay, since Mohamed, sorry, we cannot invite you on stage, so this can be done in a while in the discussion room, because we have another question from Arpit. Actually, question one, in addition, interesting talk, but two questions. Question one, in addition to abstract state machine and counterexample, what other techniques could be used for providing explanation to human operators? If you can give some examples.
I actually, there is some work on, for example, by Dimitra Giannakopoulos and their group, and they provide a synthesis of the model of the system, not to provide explanation, a simplified explanation about the behavior of a machine. So, and this refers to simplified model. However, the work has not been used to provide explanation for a specific violation of security requirements. The other aspect is that it's funnily enough, although abstract state machine have been used to support human operators and create a bridge between the requirements and the system operation, it's funnily enough, their development, they've not been used for providing explanation, and which I found it quite interesting, and some avenues that in potential avenues that can be explored, especially if you think about the fact that human operators needs more and more to be working with robots. This is called cobot. So cobot are really robots that are made to cooperate with humans.
Okay.
So I'm afraid there is not a lot of work in that respect, especially to provide explanation about system behavior. There is a lot of work, for example, that has been provided also to describe and justify the choices made by a Markov decision process. And that those explanations refer to future state of the system and future rewards that the system expects depending on decision that is taken. However, the main point of that is that these approaches do not tailor the explanation depending, for example, on the situation. For example, a requirement is violated, there is a security threat. And so there is still no way to tailor the generation of an explanation depending on the specific situation, for example, the requirements that is violated, as well as the expertise of the human operators and the time that the operators have to perform a decision. And we don't have answer for that.
Exactly, and I guess the challenge is to provide intuitive explanation in the real time. This is actually right.
Yeah, the real time depends also. The first is how to select the strategy. How do we select a strategy to abstract? How abstract should be the model in order to comply with, for example, the cognitive capacity of the operator. And so these are interesting aspects at the border between formal methods and also human-computer interaction that will be really interesting to explore and needs more exploration.
And there's a second question by Arpit. How easy or difficult is to specify properties for cyber-physical system?
I don't know if it's a matter of difficulties. It's a matter of expressing properties. For example, security requirements. In my experience, of course, the definition of security requirements follow the same by graph notation. So it doesn't differ from other requirements specific. I don't think there are difficulties in specifying security properties compared to for cyber physical system. I think the challenge is how to represent the system and have a representation that allows to reason about the cause-effect relationship between events in the cyberspace and the physical space, and vice versa.
Okay. And and Oana is asking. Okay, so thanks for the interesting talk, and asking if any shortcomings of BigGraphs.
There are many shortcomings. So there are many shortcomings.
That you'd like.
I'm going to mention some. So first thing is that unfortunately there is not, at the time when we did the work, now there is more support, but at the time when we did the work there was not a lot of support to, for example, generate a label transition system from the reaction rules and the specification of the system using BigGraphs. So that was the first problem. But the nice things why we chose BigGraph is that they embed the containment, the connectivity inside the language itself. So you don't have to specify these properties using the characteristics that are provided by the language, but they are provided by construction. So the difficulties is the lack of tool support, which now has been quite overcome, because there is a Michele Sevegnani, for example, a researcher based in Glasgow, who
We are moving to the